So now I'm gonna start learning the PyTorch stuff.
Tensor with random values by saying torch.rand and then give it the size. So let's say 2 by 2. And let's print our tensor again. We can also, the same like in NumPy, we can say torch.zeros. So this will put all zeros in it, or we can say torch.ones. So this will put ones in all the items. Then we can also give it a specific data type. So first of all, we can have a look at the data type by saying x.dtype. So if we run this, then we see by default it's a float 32, but we can also give it the dtype parameter. And here we can say, for example, torch.int. So now it's all integers, or we can say torch.double. Now it has doubles. Or we can also say, for example, float 16 just. Yeah. And now if you want to have a look at the size, we can do this by saying x.size, and this is a function, so we have to use parentheses. So this will print the size of it. And we can also construct a tensor from data, so for example from a Python list. So for example here we can say x equals torch.tensor, and then here we put a list with some elements, so let's say 2.5, 0.1, and then print our tensor. So this is also how we can create y dot and then add underscore x and then print y. So this will modify our y numpy arrays. So let's say we have a tensor of size, let's say 5 by 3, and let's print this first. And now I'll print x. And now, for example, we can simply, or we can get all rows but only one column. So let's use slicing. So we here use a colon for all the rows but only the column 0. So let's print the whole tensor and only this. So here we see we have only the first column but all the rows. Or we can just say, for example, let's use the row number 1 but all columns. So this would print the second row and all the columns. Then we can also just get one element, so the element at position 1, 1. So this would be this value. And by the way, right now
So the first value is the rows, the second is the columns.
Prints the tensor. And if we have a tensor with only one element, we can also say, we can call the dot item method. So this will get the actual value, but be careful, you can only use this if you have only one element in your tensor. So this will get the actual value. And yeah, now let's talk about reshaping a tensor. So let's say we have a tensor of size, let's say 4 by 4, and print our tensor. And now if we want to reshape it, then we can do this by saying, or by calling the view method. So we say y equals x.view and then give it a size. So let's say we only want one dimension now. So let's print y. So now it's only a 1D vector. And of course the number of elements must still be the same. So here we have 4 by 4. So in total it's also 16 values. And for example, if we don't want to put the dimension or the value in one dimension, and we can simply say -1 and then specify the other dimension, and PyTorch will automatically determine the right size for it. So now it must be a 2 by 8 tensor. So we can also print the size again to have a look at the size. So this is size 2 by 8, so it's correctly determined the size. If we put a -1 here. So yeah, this is how we can resize tensors. And now let's talk about converting from NumPy to a torch tensor and vice versa. So this is very easy. So first of all, let's import NumPy again. Or
I think that's a good question to ask. What's the difference between NumPy and tensors?
import NumPy as np. And I think I have to, oh no, it's already installed here. So let's create a tensor first. So a equals torch dot, and let's create a tensor with ones of size 5. So let's print our tensor. And now if we want to have a NumPy array, we can simply say b equals a dot NumPy and then print b. So now we have a NumPy array. So if we print the type of b, and then this will see, and this will print that we have a NumPy ND array. So yeah, this is how we can create from a tensor to a NumPy array. But now we have to be careful, because if the tensor is on the CPU and not the GPU, then both objects will share the same memory location. So
Yeah, so I guess this is probably the difference. NumPy uses CPU and Torch uses GPU.
this means that if we change one, we will also change the other. So for example, if we print, or if we modify b or a in place by saying a dot
GPU is faster for matrix multiplication and operations.
add underscore, remember all the underscore functions will modify our variable in place, and add 1. So if we add 1 to each element, and now first let's have a look at our a tensor, and now let's also have a look at our b NumPy array, then we see that it also added +1 to each of the elements here because they both point to the same memory location. So be careful here. And yeah, if you want to do it the other way around, so if you have a numpy array in the beginning, so let's say a equals numpy ones of size 5, and then print a. And now you want each element, so now print our, and this will ones. And now if you do an so then again we would have to move it back.
Hello and welcome to this episode. So in this video I'm going to show you NumPy and PyTorch. But just to give you a heads up, I want to let you understand that after this video, the subsequent teachings are going to happen through screen recordings instead of the classroom experience that you're having here. And the reason is, just like I kept promising, we needed to learn all those things we've learned up to this point, just so we have the foundations right. And now it is time for us to actually start getting our hands dirty. And because NumPy and PyTorch are very important in the machine learning landscape, I'm going to spend quite a few number of videos explaining the details of how to do vectorized implementations of certain calculations using NumPy and PyTorch. So just in case you realize that the subsequent videos after this video isn't giving you the classroom experience, I don't want you to feel like it has ended. It hasn't. It is because we are going to get practical. We are going to do some hands-on coding. So I would want to code and record my screen and show you how things are done. And then after teaching you about NumPy and PyTorch, we will come back to the classroom experience as and when it is required. So to cut things short for you, what is NumPy, what is PyTorch, how are they related? So NumPy is basically a Python wrapper around some C code that has been written to help you do some vectorized calculations, okay? So up to this point, you know what a vector is. Now, if I have, let's say, a million numbers, a vector of million numbers, to add to another million, a vector of million numbers, in vanilla Python, you have to write a for loop, and depending on how well you understand Python, you might end up using a for loop inside a for loop, just so you can sum things up, okay? Now, what NumPy does for you, and PyTorch also does for you, is it helps you to do vectorized calculations, vectorized implementation of the common calculations that we do in deep learning. So, for example, if I have a vector A to be equal to 1, 2, 3, and then I have a vector B to be equal to 4, 5, 6. Now, if I do A plus B, what's going to happen is NumPy or PyTorch is going to do element-wise summation and then give me the resulting vector. So this is going to be 1 plus 4, 5, 7, and then 9. So you can see that it helps you to write code, treating these vectors as though they were values that contained single data points, okay? But in actual sense, they are vectors. And so what NumPy or PyTorch helps you to do is to have vectorized implementations of certain common calculations that we do when GPUs with CUDA. And it also supports automatic gradient calculations, something called autograd. I mean, for now you won't understand everything, but once we get our hands dirty and then we start coding, you understand what I'm talking about. But network from scratch with PyTorch without even using the neural network modules that comes with it. But of course, you don't want to build everything from scratch, so when it is necessary, you use them. But the essence of this video and the subsequent screen recordings that will come after this video is to show you how to use NumPy and PyTorch to achieve vectorized calculations or vectorized implementation of certain common calculations, and not knowing calculus can be a limitation. But also convert a PyTorch tensor.
Welcome to Computational Physics for Absolute Beginners, Episode 1. My name is Brian, and I am creating these tutorials with the goal of helping physics students who are encountering programming, coding, computation for the first time, and helping you get on board with everything you need to get started in whatever it is you're doing in your physics class using computational physics. In order to complete this tutorial, you will need access to the Python Tutorial 1 Computations and Variables. You'll need to open it in a Jupyter Notebook environment. There are different ways of getting access to Jupyter, and I will let your instructor give you that orientation as it depends on what their preferences are, what your university's requirements are, etc. But once you get into Jupyter, you'll have it open in a web browser like this, and it works just like a file system. You can click on any of the files here. We're going to start here with Python Tutorial 1, Computations and Variables, and in this video, I'm just going to walk you through some of the highlights of this tutorial. A Jupyter Notebook is composed of two types of cells. There are Markdown cells. This is text that I am with this hash mark, the number sign, the pound sign, shift 3. The computer will ignore. This is what we call a comment. It's where we, the humans, answer here with 5. Next line, I see a 3 minus 2. I'm here to Math World, where you can refresh yourself on Taylor series. But the basic idea is that if you want to take a function and make an approximate version of it, you can do that by having the function at a certain value c plus the first derivative plus the evaluated at c. 3 halves, we flip the sign again. So I have a 1 over 1 factorial. There's that piece. I have a 1 over 2. There's that piece. Line 7 and 8. Paste them here at line 11. Difficult time keeping track of what each of these 2's is, what each of the 1's is, whether it's supposed to be a plus 3. All I have to do now is, when I think about it, is instead
This is too much for beginners. It's not gonna talk about complex equations, probably. think what I'm gonna do is watch this video, then start watching this playlist. Then as I watch the playlist, I'm gonna pause and try to figure out how to compute the stuff that he talks about instead of watching videos.
Hi, I'm Dan Fleisch.
And I'm gonna read this library to see how to do that.
When people hear that the subject of my new student's guide is vectors and tensors, a reasonably high percentage of them have the same question. What's a tensor? My goal for this video is to take about 12 minutes to answer that question, not using a bunch of mathematical equations, but instead some simple household objects, including children's blocks, small arrows, a couple of pieces of cardboard, and a pointed stick. I think the very best route to understanding tensors is to begin by making sure that you're solid on your understanding of vectors. If you've taken any college-level physics or engineering, you probably think of a vector as something like this: an arrow representing a quantity that has both magnitude and direction, wherein the length of the arrow is proportional to the magnitude of the quantity, and the orientation of the arrow tells you the direction of the quantity. This could represent the force of gravity on an object, or the strength and direction of the Earth's magnetic field, or the velocity of a particle in a flowing fluid. But vectors can represent other things as well, such as an area. How does a vector represent an area? It's pretty straightforward. You simply make the length of the vector proportional to the amount of the area, the number of square meters in the area. And then you make the direction of the arrow perpendicular to the surface. So, in that way, this can represent an area as well. So vectors can represent lots of things. But if you want to take this step beyond thinking of vectors as representing quantities with magnitude and direction, to understanding that vectors are members of a wider class of object called tensors, then you have to make sure you understand vector components and basis vectors. If you're even going to think about the components of a vector, you better get yourself one of these. This represents a coordinate system. In this case, I picked the simplest one: an x-axis, a y-axis, and a z-axis, all meeting at right angles. This represents the Cartesian coordinate system. And the thing to remember about coordinate systems is they come along with coordinate basis vectors. You probably ran into these as unit vectors. And the thing to remember about these little guys is they have a length of 1. One what? One of whatever the units are that you're going to express the length of your vector in. And the direction of the basis vectors, or unit vectors, is in the direction of the coordinate axes. So this might represent the unit vector in the x direction. That's often called x with a little hat over it, or sometimes I hat. That's the x hat unit vector. It points in the direction of increasing x coordinate. Likewise, the y hat, sometimes called the j hat unit vector, points in the direction of increasing y. And the z hat, or k hat unit vector, points in the direction of increasing z. Once you have the coordinate system and the unit vectors in place, now you're in a position to find the components of your vector. Component of this vector. Standing perpendicularly, representation.
This is too basic. Just gonna talk about stuff that I probably already know.
Might you need such a representation? Consider, for example, the forces inside a solid object. Inside that object, you can imagine surfaces whose area vectors point in the x, or in the y, or in the z direction. And on each of those types of surface, there might be a force that has a component in the x, or in the y, or in the z direction. So to fully characterize all the possible forces on all the possible surfaces, you need 9 components, each with 2 indices referring to 2 basis vectors. 27 components, each pertaining to 7 components vectors.
So I'm gonna watch the playlist.
First real video in my series on tensors. The previous 2 videos were mostly on giving motivation and background on tensors. In this video, we're going to get started doing some actual real math. So the first thing we're going to learn is forward and backward transformations. These are the rules that let us move back and forth between different coordinate systems. I mentioned in the previous videos that tensors are invariant under a coordinate system change, so understanding how to move back and forth between coordinate systems is going to be really important for understanding tensors. Okay, so let's start off with the forward transformation. So I have two-dimensional coordinate systems here, the old basis E1 and E2, and the new basis E1 tilde and E2 tilde. So remember from linear algebra that the word basis just means a set of vectors that give us the main coordinate directions for our space. So we have the old and new coordinate systems, or the old and new basis. So the forward transformation will move us from the old basis to the new basis. So how does that work? Well, all we need to do is to build the new basis vectors out of the old basis vectors. So let's start with E1 tilde here. How do we build E1 tilde out of E1 and E2? Well, it looks like we need 2 E1 vectors and 1 E2 vector. So I'll just write that in here. Now, what about E2 tilde? So it looks like we need half of E1, but it's in the
So I think I already need to pause here. I think I'm gonna create a function for each one. the problem is I'm not sure. I think these vectors are two-dimensional based on the video. If I have a one-element tensor, for example, by aggregating all values of a tensor into one value, you can convert it to a Python numerical value using an item. Base operations, bridge of NumPy. Tensors on the CPU and NumPy arrays can share their underlying memory allocations, and changing one will change the other. So torch.ones creates a vector with 5 ones. So I guess I'm gonna use that for defining E1 and E2. Which is gonna be T equals torch once with 2 instead of 5. Actually, I'm gonna make the size dependent on the variable that is passed as an argument. And I'm gonna return this tensor, which is really simple. Then I'm gonna do the same thing for E2. So basically the value, the magnitude of the vector is gonna depend on how much you wanna make it. I also have to think about if I'm gonna put, I think I'm gonna put the components into a file and do the calculations into another one. So I'm gonna create a file called calculations. Part NumPy, NP, part torch, parts video show. Then here is gonna start talking about neural networks, I guess. So the tensor part is actually really simple. And I guess I can use NumPy as well to build vectors instead of PyTorch. Then I'm gonna create a function called ET, which stands for E tilde, which is gonna be, we'll put X and Y as arguments. X times E1. The issue here is that I don't know how to make the size of this. How to pass the sizes into the other function. Maybe I don't need to.
Opposite direction, so that's actually minus a half. And then we need a quarter of E2. So I'll just write those in. All right, so what we've done is we've written the new basis vectors as linear combinations of the old basis vectors. And if I wanted to, I could store these four numbers in a 2x2 matrix called F for forward. And so that's really it. That's the entire forward transformation. If we know
So let me think about this. So I have two vectors. I have a function for each vector. Then I have another function that takes two arguments and sums the vector based on these two arguments. Now maybe I need to do that forward E. And then I take as arguments the vectors. Oh, it's actually this is not gonna work. Can make it E1, E2. So the forward E takes two arguments. And maybe this is not the best way. Should do this. Don't have a lot of practice building classes and functions. So it might take me some time to decide which is the best way to do it.
the matrix F, then we know everything we need to know to construct the new basis from the old basis. Okay, so what about backward transformations? As you'd expect, it's basically just the same thing, but in reverse. So we build the old basis vectors using the new basis vectors. So how do we build E1 using E1 tilde and E2 tilde? It's a little more confusing this time, but it looks like we need a quarter of E1 tilde and exactly 1 of E2 tilde, but facing the opposite direction, so it's actually -1. So I'll just write those in. And what about E2? It looks like we need a half of E1 tilde and 2 E2 tildes. And again, we can store these 4 numbers in a 2x2 matrix called B, B for backward, and that's it. That's the backward transformation. So if we know the matrix B, we know everything we need to construct the old basis from the new basis. Now you might be thinking here, we have the matrix F and we have the matrix B. Are these really two different things? They kind of do the same job but in opposite directions, so are they really so different? Well, let's see what happens when we multiply them. So this might actually be a good exercise for you to review matrix multiplication. To multiply two matrices, we write them like this, and to get this entry of the resulting matrix, we take the dot product of this row vector and this column vector. So in this case, it's 2 times a quarter plus 1 times a half. So that's just a half plus a half, which equals 1. All right, so I'm going to let you do the other 3 entries, but what you'll find is you get this matrix here with 1s along the diagonal and 0s everywhere else, and that is, of course, the identity matrix. So what this really means is that F and B are inverses, or another way of saying that is that B is equal to F inverse. So why am I using 2 different letters here? Why use F and B when I could use F and F inverse? Well, just visually, I personally find it easier to tell the difference between F and B than between F and F with a tiny little -1 up here. So even though B is equal to F inverse, I'm just going to keep writing B. Okay, so that was an example in 2 dimensions. What if we want to generalize this to n dimensions? Well, it's basically the same process. We have n old basis vectors, e1, e2, all the way to en, and we have n new basis vectors, e1 tilde, e2 tilde, all the way to en tilde. And we need to decide how to build the new basis vectors out of the old basis vectors. And we do that just by choosing the right coefficients so that all of these linear combinations work properly. And again, we can write all these coefficients in a matrix. This time it would be an n by n matrix instead of a 2x2 matrix. And so that's our matrix F. Now, writing out all these equations is kind of annoying, so let's see if we can find a better way to write this. So if I wanted to build ei tilde vectors out of the ej vectors, what I would want to do is write ei tilde as sum of the ej vectors, but I still need to decide on the coefficients. So what would those be? Well, if you look up here, you'll see that f21 tells us how much of e1 makes up e2 tilde. Okay, so f21 tells us how much of e1 makes up e2 tilde. And over here, f1n tells us how much of en is inside e1 tilde. So really the coefficient I want here is fij. Fij tells us how much of ej makes up ei tilde. So really this summation summarizes all of the above equations nice and simply. So this is the forward transformation in n dimensions. Now for the backward transformations, we can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. We can write these coefficients in an n by n matrix called B. And we can summarize all these equations using a summation. Ei is equal to the sum of ej tildes with the coefficients being bij. So that's the backward transformation in n dimensions. Okay, so we have the forward and backward transformations. Can we prove once again that they are inverses? Well, I'll start with the backward transformation just here. And if you'll notice, the forward transformation gives us an equation for ej tilde. So I'm just going to substitute that in for ej tilde here, and we get this. And rearranging some of the summation signs, we get this. Okay, so let's just put this on a new slide here. So looking at the formula, what's going on here is that we're building the old basis vectors using a summation of the old basis vectors. And what we need to do is we need to decide what this middle part of the equation should be. So why don't you pause the video and take a few seconds to think about what this middle part should be if we want these.
I have no idea. Not sure if I understand this very well.
With a tiny little -1 up here. So even though b is equal to f inverse, I'm just going to keep writing b. Okay, so that was an example in 2 dimensions. What if we want to generalize this to n dimensions? Well, it's basically the same process. We have n old basis vectors, e1, e2, all the way to en, and we have n new basis vectors, e1 tilde, e2 tilde, all the way to en tilde. And we need to decide how to build the new basis vectors out of the old basis vectors. And we do that just by choosing the right coefficients so that all of these linear combinations work properly. And again, we can write all these coefficients in a matrix. This time it would be an n by n matrix instead of a 2x2 matrix. And so that's our matrix F. Now writing out all these equations is kind of annoying, so let's see if we can find a better way to write this.
It's pretty much using a bunch of vectors to translate into different vectors using different coefficients.
So if I wanted to build ei tilde vectors out of the ej vectors, what I would want to do is write ei tilde as sum of the ej vectors, but I still need to decide on the coefficients. So what would those be? Well, if you look up here, you'll see that f21 tells us how much of e1 makes up e2 tilde. Okay, so f21 tells us how much of e1 makes up e2 tilde. And over here, f1n tells us how much of En is inside E1 tilde. So really the coefficient I want here is Fij.
So each coefficient tells the size of each vector that makes up the E tilde show.
tells us how much of Ej makes up Ei tilde. So really this summation summarizes all of the above equations nice and simply. So this is the forward transformation in n dimensions. Now for the backward transformations, we can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. We can write these coefficients in an n by n matrix called B, and we can summarize all these equations using a summation. Ei is equal to the sum of Ej tildes with the coefficients being Bij. So that's the backward transformation in n dimensions. Okay, so we have the forward and backward transformations. Can we prove once again that they are inverses? Well, I'll start with the backward transformation.
I think I don't understand the backwards very well.
Basis vectors. So how do we build E1 using E1 tilde and E2 tilde? It's a little more confusing this time, but it looks like we need a quarter of E1 tilde and exactly 1 of E2 tilde, but facing the opposite direction, so it's actually -1. So I'll just write those in. And what about E2? It looks like we need a half of E1 tilde and 2 E2 tildes. And again, we can store these four numbers in a 2x2 matrix called B, B for backward, and that's it. That's the backward.
So backwards is decomposing E1 into the measurement of each vector that makes up the E1.
Transformation. So if we know the matrix B, we know
Which is a
everything we need to
matrix.
construct the old basis from the new basis.
So the backwards is the matrix that forms each vector. Each row is going to be the E1, E2, E3, so forth.
Now you might
Dimensions.
be thinking here, we have the matrix F and we have the matrix B. Are these really two different things? They kind of do the same job but in opposite directions, so are they really so different? Well, let's see what happens when we multiply them. So this might actually be a good exercise for you to review matrix multiplication. To multiply two matrices, we write them like this, and to get this entry of the resulting matrix, we take the dot product of this row vector and this column vector. So in this case, it's 2 times a quarter plus 1 times a half. So that's just a half plus a half, which equals 1. All right, so I'm going to let you do the other three entries, but what you'll find is you get this matrix here with 1s along the diagonal and 0s everywhere else, and that is, of course, the identity matrix. So what this really means is that F and B are inverses, or another way of saying that is that B is equal to F inverse. So why am I using two different letters here? Why use F and B when I could use F and F inverse? Well, just visually, I personally find it easier to tell the difference between F and B than between F and F with a tiny little -1 up here. So even though B is equal to F inverse, I'm just going to keep writing B. Okay, so that was an example in 2 dimensions. What if we want to generalize this to n dimensions? Well, it's basically the same process. We have n old basis vectors, E1, E2, all.
So the issue here is that I'm trying to think about how to compute this in Python. It's kind of hard to think about it because I'm not exactly sure how it's gonna use that in the future. So what's the best way to design the function? Go forward, E has to be a matrix with the coefficients multiplying the vectors. I think I can erase the E tilde function. Because each E tilde is just gonna be the linear combination of the vectors. So I think I have to see how to make a matrix with PyTorch.
Okay, so now we have all of our dependencies installed, like PyTorch, Python, NumPy. Now we can get to PyTorch fundamentals. And the first thing I want to talk about is matrices. So let's move on to a brief introduction. A matrix is just basically a rectangular array of numbers, where in PyTorch, they're called tensors, and if you're familiar with NumPy, they're called ND arrays. Now, a 2 times 2 matrix is basically just this table of numbers 1, 1, 1, 1, where 2 represents the row, and the second number represents the column. Now, a 2 times 3 matrix would then be like that, because you have 2 rows and 3 columns. Now, normally, if you're familiar with Python, when you want to create a matrix, what you need to do is to feed the matrix. You need to pass the matrix argument with a list. So what happens is that we import NumPy first. And to create a 2 times 2 array, which we want 1, 2, 3, 4, we just need to use nested lists. So we have a list here, as you can see, the green parts. That's the main list, and then you have 2 lists within here. So when we print it, we get 1, 2 within one list, 3, 4 within one list, and you get a whole list. Now, when we pass this particular list, which is ARR, into numpy.array, we have a 2 times 2 array here. This is how we can create a 2 times 2 array comprising 1, 2, 3, 4 in NumPy. Now, what happens in PyTorch? Now, in Torch, I believe it is very similar to NumPy. So when we do it, we just need to import Torch, and we convert it to a PyTorch tensor by doing torch.tensorArray. That's all. So you see, the only difference here is that we change NumPy to Torch, and that is how we can create a tensor in PyTorch. Now, if we want to create matrices with default values in NumPy, what we normally do is that, let's say we want to create a 2 by 2 matrix, a 2 by 2 matrix comprising of ones. So we will normally do this, numpy.ones, 2, 2, and we have 1, 1, 1, 1. And what happens in Torch? Again, the syntax is very strikingly similar in the sense that we just replace NP with Torch, and you get 1, 1, 1, 1 of 2 times 2 size. Now, what happens if you want an array of random numbers? So again, I want to keep things consistent, and I want to create an array of random numbers in a matrix of size 2 times 2. And how we can do this in NumPy, if you're familiar with it, is numpy.random.ran. Now, in Torch, if you want to have a random numbers filling up a matrix of size 2 times 2, all you need to do is just use torch.ran 2, 2. And that is it to it. Now, we will be talking about how we can, when we use torch.ran, how we can replicate this exact same matrix numbers every single time we run torch.ran.
This is breaking my head.
In this video of Bug Bites Shorts, we're going to take a look at the at operator in Python. It's the mat mul outputting PyTorch's torch numbers. These together, we would use numpy.dot and we would get the dot product. But what we can do instead is we can use the at operator to multiply those two matrices together. So we get the dot product here using the matrix code. We can basically and switch the NumPy code. Torch.ran then will give us some.
I think I'm gonna have to look to continue watching a little bit more of the playlist to really think about how to structure the functions. This seems like a good video to watch.
Hello all, my name is Krishnaik and welcome to my YouTube channel. So guys, this is the tutorial 2 of PyTorch, and in this particular video we are going to understand what exactly is tensors. We are going to perform some of the operations that can be performed on tensors, and then I'm going to actually show you with the help of PyTorch library. So guys, if you have already used TensorFlow, I think tensors should be very, very much easier to understand because it is the basic unit, in the algebraic operations that you're actually performing. And trust me, because of the tensors, we are also being able to use the power of the GPU, where we do a lot of parallel pre-processing, right? Or parallel processing itself. Now going to my previous video, guys, I hope you all know that we had created one PyTorch_env.yml and we installed this libraries. We created an environment env PyTorch. We installed PyTorch, Torch Vision, and other libraries like scikit-learn, Seaborn, matplotlib, pandas, and numpy because I'm going to perform a lot of operations onto this. And this was basically the GitHub link. If you have not done, again, the YouTube link will be given in the description of this particular video. Now let us go ahead and try to understand what exactly is tensors. So guys, tensors is a generalization of vectors and matrices and is easily understood as a multi-dimensional array, right? So it is a term and set of techniques known in machine learning and in the training and operation of deep learning models and can be described in the terms of tensors, right? In many cases, tensors are used as a replacement for NumPy to use the power of GPUs. That is the main reason. And PyTorch, they have extensively used tensors because in the upcoming lessons, you'll be seeing that when I'll be doing some back propagations, I'll be performing a lot of operations with the help of these particular tensors. It will be pretty much amazing and you'll be able to understand. So, and as it is said over here, guys, it is a replacement for NumPy, right? So one more point I really want to add is that tensors are a type of data structure used in linear algebra like vectors and matrices, and you can calculate arithmetic operation with tensors. And if you don't know, guys, internally ANN, artificial neural networks, they are hidden layers, hidden nodes, right? Weights are getting assigned. The inputs is multiplied by the weights, and a bias is added, and an activation function is applied on top of that. So all this kind of arithmetic matrix operation can be performed easily with the help of these particular tensors, and it will be pretty much fast. Okay, pretty much fast. We'll be seeing that.
I guess I can also search for transformation. So the function has to take a bunch of it has to take a list of answers of vectors and a list of parameters and transform them and multiply them. So torch dot dots. I'm not sure how to do matrix multiplication using torch, but backwards would be the other way around, I guess. Or it would be E transpose times N.
Learning about the basic.
But in this video, what we'll do is that we'll just start with the basics. We'll try to understand what exactly is tensors, how we can create a tensors, how we can create it from a NumPy array, what are the different types of matrix multiplication you can do, and all those things we'll actually understand from this. So first of all, I am going to import torch. And if you know, guys, in my previous session, we had actually, this is basically the single dimensional array. Now in this step, we are going to convert the NumPy to PyTorch tensors. How to do that? See, guys, in torch, you basically have a function which is called as from_NumPy. Now if you press shift tab, okay, always try to press shift tab and see the definition of each and every function, guys. There are tons of functions that are used in PyTorch. So it is pretty much important that you understand from this. By pressing shift tab, you'll be getting all the information. So here it says that it creates a class tensor from a class NumPy ND array. This is pretty much important, guys. See, the return tensor and the torch, whenever you're using it, will be can basically write like this, :2. I hope everybody is familiar. If you know NumPy, pandas, at that time, this kind of indexing is pretty much common. Now here you can see that I have actually picked up 3 and 4. Suppose if I raise, guys, yes, it will happen because it is using the same memory location. So here you can see both are having the same values, right? Now what to do if I want to prevent this? So here we have a different way of creating tensors, which will just do a copy of that particular array. And that particular function is basically tensor, right? So initially it was from_NumPy, torch.from_NumPy, but this time we will be using torch.tensor. So if I go and press shift tab, you will be able to see over here, it always copies from the attribute or the data that we are actually providing, right? So it is basically fixing that particular problem. So if I create like this, now you can see that these are all my elements. Suppose I say that in my third index, replace it with 120, and then I'm trying to print tensor array, and then I'm trying to print array. In the array, I'm having 100 right now, okay? So once I execute this, you'll be able to see that only the changes that happened in the tensor array, not in the other array itself, right? Now there are also different ways how we can create tensors by using the inbuilt function that are present inside Torch. So here we have some of the inbuilt functions like zeros, same like NumPy guys. Zeros we have ones, right? Here we just need to give the shape of the matrix how we want, and then coming to the arithmetic operations, what are the different arithmetic operations we will do? Because understand guys, if I am actually trying to create an ANN, that is artificial neural network, there we will be giving the inputs, right, to our hidden layers, right? So there will be a weight that will get initialized. So I have to multiply that inputs with the weights, add a bias. So this type of operations you should be familiar with, right? Where how we do the dot operation, how we do the arithmetic operation, how we do the addition operation and all. So coming up to this, the first arithmetic operation, we are basically going to write torch.tensor. Suppose I have initialized two tensors over here, one with the element 3, 4, 5 and other with the element 4, 5, 6. And remember guys, this indexing can also be done for two-dimensional arrays. Now, how do you create a two-dimensional arrays in this? Just let me show you guys. Okay, so two-dimensional arrays, what I'm going to do is that I'm just going to create something like this. Suppose if I write np.arrange, okay, and suppose if I say 0, 15, right, and I say reshape to 5, 3, right? So this will actually give me an array of 5 rows and 3 columns. Now, if I try to convert this into torch.tensor, right, like this, right, this will actually get converted into torch. Now, if I store that in a variable, you can see that if I store it in a variable a, and suppose I want to perform any indexing in this two-dimensional, because this is two-dimensional, right? I've given two shapes like 5, 3. You can also convert this into 3-dimensional. Suppose I just want to pick up all these elements, the first column elements, I can basically write something like this: colon, comma 1, right? Or colon, comma 0, sorry, 0th index. So I'm basically getting 0, 3, 6, 9, 12, right? I can also write 0, 2 if I want to get two first columns. I can also write like this. So the indexing technique is almost same, guys. No need to worry much about the indexing techniques, right? It is same like NumPy. Exactly same like NumPy, nothing to worry as such. Now guys, I'm going to perform some operation. The first operation that I'm actually going to do is a simple arithmetic operation. So here I've actually created tensor with 3, 4, 5 as element, and here I've actually created 4, 5, 6. If I really want to add like this, I can basically write a plus b. Now when I write a plus b, automatically the operation will take place where this 4 will get added to 3, 5 will get added to 4, 6 will get added to 5, right? So that same element we are getting over here, 7, 9, 11, right? 4 plus 3 is 7, 5 plus 4 is 9, 6 plus 5 is 11, right? Then we also have an inbuilt function if you want to perform the same operation, right? How we got this. And there is an inbuilt function which is called as torch.add. So if I see over here, it basically says that add the scalar attribute to each other elements of the input attribute, right? So this is pretty much simple and we are getting the same output, right? Now similarly, suppose I want to add this and store it in some other variable. Now if I want to store it in some other variable, first of all, I need to make sure that I create that variable with the same shape, whatever the output shape that we are actually getting. So here what I've done is that I've used C and I've actually initialized and tensor, probably I have to execute this. Now, if I go and see, then you can see that I'm getting 7, 9, 11 because of this particular out, because I've told that whatever addition you are doing, you just give that value to the variable C, right? So because of this, you can actually see I'm getting an output over here, right? Now, some more operation. What I can do is that I can use this add, and on top of that, I can use another inbuilt function like sum. So what it will do? First of all, it will add like this 4 plus 3. You can see what kind of operation it will do. First it will add 4 plus 3, 4 plus get initialized to y. I'm actually getting the output as 62. So 30 plus 20 plus 12. Pretty much simple. Just try it by yourself, guys. It is pretty much simple itself. The next is basically a matrix multiplication. You can also do matrix multiplication, and there is an inbuilt function again, like matmul. Okay, so this matmul, and this is if you remember, guys, this all inbuilt functions are similar to NumPy, right? So it is.
So matmos, matrix multiplication. So I think there's gonna be a matrix multiplication for propagation between e values and whatever thing, whatever constant each one has, depending on the vector. But it gets confusing because e is already gonna have it's already gonna be a two-dimensional thing.
So in matrix multiplication, you have matmul function, you have this function, and you have x at the rate y. What does this basically mean? Suppose if you want to do matrix multiplication of x comma y, so this is basically the output. I hope you know how to do matrix multiplication. It's simple maths, guys. You have also studied it 10th standard. Instead of using matmul, I can also use this is the short form of matrix multiplication. Also you can use, and if you give x comma y, you're basically getting the output. Similarly, instead of this, you can also write x at the rate y. Okay, so this is x at the rate y. So you're basically doing a matrix multiplication between x and y. That is what this x at the rate y basically means. So yes, guys, this was some of the basic operation with respect to tensors. And now in my next video, I'll try to show you how you can do a lot of functionalities which is involved in ANN, like backpropagation, how you can find out the derivative with the help of PyTorch. That we are going to see. Please make sure that, guys, you understand the theoretical understanding of deep learning. If you don't know, please make sure go and follow my deep learning playlist over there. Okay. I'm not just going to take the theoretical things, guys. I'm specifically going to show you how you can perform most of the operation, all the operations that are involved in ANN, CNN, and RNN. So yes, guys, this was all about this particular video. I hope you like it. Please do subscribe to the channel if you're not already subscribed. I'll see you in the next video. Have a great day ahead. Thank you one and all. Bye bye.
Hey guys, welcome back to the channel and this new tutorial on PyTorch. So in previous video we learned about like indexing and slicing. Also we have seen like how we can do NumPy array to tensor, and then how we can convert it back from tensor to NumPy. In this video we will learn about like how we can change the shape or size of a tensor. Okay. So let us dive in and start like what are the basic operations that we can use, or basic functions that we can use to modify the shape of a tensor. Okay. So let us create a simple tensor. Let us say x is equal to torch dot tensor, and let us create a simple tensor 1, 2, 3, 4, 5, 6. Okay. Now let us print x dot shape. So what it will be? It will be simply like a vector. Okay. So let us run and see it. So you see it's simply like size 6 vector. Okay. Now if simply I will add a further dimension, which will be so like 1 cross 6 now. Okay. So now let us run and see it. So you see it is now 1 cross 6. So the first method that we will learn is squeeze and unsqueeze. Okay. So it is mainly used to add a 0 dimension shape or remove a 0 dimension shape. Okay. For example, if you want to remove this shape or this dimension which doesn't have any elements in the dimension, we can simply use x dot squeeze. Okay. So we can simply say x is equal to x dot squeeze. Okay. And now the shape of x would be simply a vector which will have 6 elements. Okay. So now if we run it, it will be simply a vector of 6 elements. It won't have the dimension that has just no elements. Okay. And this is mainly useful when we get a tensor where it has many dimensions, just one, and then we want to remove it. In those cases, it is useful. Okay. Also, squeeze is simply like if there are many one-dimensional shapes, it will remove all of them. For example, if there are simply add one more dimension here, and then it will be like 1 cross 1 cross 6. Okay. So if I want to squeeze it, it will be of the shape, you see, 1 cross 1 cross 6. Now if you want to simply squeeze just one dimension and keep the others, we simply specify the dimension we want to squeeze. For example, if I want to say squeeze just 1, then it will squeeze just 1, and then we will get 1 cross 6. Okay. So you see. Now let's look at like how we can use unsqueeze. Unsqueeze is like a reverse of squeeze. So in that we will add extra dimension. Okay. So let us create another tensor torch dot tensor, and let us say we have a simple vector 1, 2, 3, 4, 5. Okay. Now when we say x is equal to, let us print x dot save, and now let us say x is equal to x dot unsqueeze. Okay. And let us add so it requires a dimension where we want to add, so let us say 1, and if we will print now the shape, so here we have like a tensor which is a vector actually, and then we unsqueeze it in dimension 1, so it will have 5 cross 1. Okay. So let us run and see it. So let us comment this out. So you see it is 5 element vector, and then we have a tensor which has another dimension. Okay. Next, let us look at another operation which modifies the shape of the tensor, which is transpose. Okay. And in transpose we have two methods. One is tensor.t, and then we have tensor.transpose. Okay. And the basic difference in between tensor.t and tensor.transpose is like tensor.t is only applied on a 2-dimensional tensor. We cannot apply it multi-dimensional tensor. Okay. And let's see with examples. So let's say we have a tensor x is equal to torch.tensor 1, 2, 3, 4. Now let us create another dimension, say 5, 6, 7, 8. Okay. Now if I will say print x dot shape, and let us call x is equal.
The hardest part about this is that I'm trying to think about how to incorporate this, how to design the function given the playlist in mind. I can't figure out a way that, because it seems like it's always going to be variable the amount of f's it has and the amount of e's, which each of these e's is going to be a vector, and I'm not sure the dimensions of this vector. Maybe it's two-dimensional, even the video, but it might be three-dimensional because of space. Or it might be even more dimensionals. So each of these is a vector itself times this and the plus everything. So this is going to be a matrix, which is the result of the multiplication of this matrix with the matrix of this e's here. But it's going to be e tilde until en tilde times f, the f matrix. And each e tilde is going to be the composition of these vectors here. So how can I put that into a function? That's the question. Because it's always going to be, function has to be dependent on the size of each vector, the size of n. So I'm not sure how to do this. What I wrote so far is a function to create a vector, simple vector. And then the function that multiplies the f matrix with this matrix. What?
All the way to en, and we have n new basis vectors, e1 tilde, e2 tilde, all the way to en tilde. And we need to decide how to build the new basis vectors out of the old basis vectors. And we do that just by choosing the right coefficients so that all of these linear combinations work properly. And again, we can write all these coefficients in a matrix. This time it would be an n by n matrix instead of a 2 by 2 matrix. And so that's our matrix F.
Because that's the thing. I could make a function that takes an argument and makes that the size of the matrix, but then each vector, each component of the matrix would be different itself, which would have to come from other functions. So in case I wanted to do this, then I would have to create a bunch of vectors first with a bunch of components and then call the function. So I'm wondering if there's a way to automate this so that I can just create everything automatically. But
now writing out all these equations,
I think I need to see more of the playlist to, maybe I'll watch the playlist, then I'll go back and try to figure out what's the best way.
So let's see if we can find a better way to write this. So if I wanted to build ei tilde vectors out of the ej vectors, what I would want to do is write ei tilde as sum of the ej vectors, but I still need to decide on the coefficients. So what would those be? Well, if you look up here, you'll see that f21 tells us how much of e1 makes up e2 tilde. Okay, so f21 tells us how much of e1 makes up e2 tilde. And over here, f1n tells us how much of en is inside e1 tilde. So really the coefficient I want here is fij. Fij tells us how much of ej makes up ei tilde. So really this summation summarizes all of the above equations nice and simply. So this is the forward transformation in n dimensions. Now for the backward transformations, we can do the same thing. We just write out all the old basis vectors as linear combinations of the new basis vectors. We can write these coefficients in an n by n matrix called B. And we can summarize all these equations using a summation. EI is
Maybe if I make a function that takes a matrix, yeah, because then I can put the numbers into the thing instead of writing each vector. And then it's automatically gonna do the transformation for me.
Is equal to the sum of ej tildes with the coefficients being bij. So that's the backward transformation in n dimensions.
Yeah,
Okay,
so it has to take two arguments, the f and e vectors. And the first argument is gonna be a matrix that is it has like vector here plus vector here plus etc. It's gonna be something like this. I wonder if I can, yeah. Cancel out. So the E is gonna be a list with the sum of vectors. Then we have to pass. That's why it's a little bit confusing. Because it can't be just the matrix. F, I think, is simple because it's just a matrix that's gonna multiply. So F is gonna be equal to a bunch of numbers. They have to be the same dimension of so this has to be the same dimensions of this. I think F is the easiest one. And I have to think about yeah, I can have a function. So I think the question I need to ask is how to make a function that takes another function arguments. Make a function that takes a matrix as an argument. These are the main questions, I think. So if I could make this one, I would, instead of having these vectors, it would be just a matrix with the vectors that I would pass on as arguments. So create a bunch of vectors using a function to create vectors. Put them on a matrix of 2 dimensions. Yes, it would have to be 2 dimensionals as well. Each line, because each one is e tilde is gonna be the sum of each one, which is gonna be one value times f. This is the forward transformation, and the backwards is gonna be E transpose times F, I guess.
So we have the forward and backward transformations. Can we prove once again that they are inverses? Well, I'll start with the backward transformation just here. And if you'll notice, the forward transformation gives us an equation for ej tilde. So I'm just going to substitute that in for ej tilde here, and we get this. And rearranging some of the summation signs, we get this. Okay, so let's just put this on a new slide here. So looking at the formula, what's going on here is that we're building the old basis vectors using a summation of the old basis vectors. And what we need to do is we need to decide what this middle part of the equation should be. So why don't you pause the video and take a few seconds to think.
Well, it's gonna be a matrix. I'm not sure. It gets confusing so fast from that part to this one. Because of all the letters, it's just too confusing.
Think about what this middle part should be if we want these equations to make sense. Okay, so what we really want at the end of the day is for E1 to equal E1, we want E2 to equal E2, and so on and so forth.
Be the identity matrix.
We don't want any extra basis vectors in here being added because that wouldn't make any sense. So what we really want is for this middle part to be 1 when I is equal to k, and we want it to be 0 when I is not equal to k. Right? That makes sense? And really, if you think about this as a matrix where I gives you the row and k gives you the column, putting 1 where I equals k means we have 1s where the row is equal to the column. So we get 1s along the diagonal line here.
That's going to be the identity matrix.
We would just get 0s everywhere else. So again, 1s along the diagonal, 0s everywhere else. Once again, we showed that multiplying f by b gives us the identity matrix. So f and b are inverses of each other. Now this behavior where we have 1 where I equals k and 0 where I doesn't equal k, this behavior ends up being so common that we give it its own symbol called the Kronecker delta. So whenever you see the Kronecker delta, just think of this relationship right here. It's a bit like telling you what the entries of the identity matrix are, where we have 1 where the row is equal to the column and 0 everywhere else. Okay, so to sum up what we learned in this video, we learned that formulas for the forward and backward transformations in n dimensions, and we also showed that the forward and backward transformations are inverses of each other, because when we multiply the f and b matrices, we get the identity matrix whose entries are given by the Kronecker delta symbol here. Hi everyone.
Yeah, so I think this is a good layout. I have a simple function that makes a vector. Then if I want, I can create a bunch of vectors and put them on a matrix to pass into the forward function. Maybe I can have another function that creates the matrix. If I pass a bunch of vectors in a list, it just reshapes the thing to a matrix, 2x2 matrix.
So I'm gonna have to apologize for this, but I actually made a mistake in the previous video that I want to correct. So with the forward transform, everything I wrote on this slide is correct, except for the forward matrix, and the forward matrix should look like this. So notice how the coefficients from the first equation end up in the first column, and the coefficients from the second equation end up in the second column. In the previous video, I wrote it out like this, and that's actually F transpose, but the correct F matrix should look like this.
And the same thing goes for the backward transform. The first equation goes into the first column, and the second equation goes into the second column. In the previous video, I also accidentally
Maybe a good thing to search is transforming list of vectors into matrix.
wrote out B transpose instead. So looking at these equations for the forward
Breadback.
transform, f12 tells us how much of E1 is in E2 tilde. And likewise, Fji tells us how much of Ej ends up in Ei tilde. In the previous video, I accidentally wrote this with Fij instead, but that's wrong. So this should be Fji. And the same goes for the backward transform. Bji tells us how much of Ej tilde ends up in Ei. So these are the correct forward and backward transforms here. And I'd just like to clarify that the actual letters I use for the indexes don't really matter. What's important here is that the index that we do the summation over is the first letter of the forward or backward transform, and it corresponds to the index of the basis vector that we're transforming. The second index of the transform corresponds to the output basis vector. Again, I apologize for making a mistake like this right at the beginning of a video series, but hopefully you aren't too confused. For the rest of the video series, I'm going to be using these equations here.
Welcome back.
I'm gonna watch one more video and then I'm gonna search for those things here. Just try to build the functions.
To the video series on tensors. In the last video, we covered forward and backward transformations, and in this video, we're going to talk about our first example of a tensor, which is the vector. So what is a vector exactly? Much like tensors, you might get different answers to that question depending on who you ask. So this is one definition you might hear. A vector is a list of numbers, or a vector is a one-dimensional array of numbers. So that's a nice, easy definition. And here are a couple examples of vectors, v and w, and they're just lists of numbers. So you probably already know if we want to add these lists together, we just add them like this, right? We just add the corresponding elements to get the new vector with elements v1 plus w1, v2 plus w2, and so on and so forth. So that's vector addition with lists. And you probably also know that we can scale vectors using a scaling constant like this. So we just take the scaling number a and give it to each number inside the list and multiply each number inside by a. So this definition of a vector is easy enough, but there is a problem. And the problem is that these list of numbers are actually vector components, not the vectors themselves. So if you'll recall, I said before that vectors are invariant under a change of coordinates, whereas vector components are not invariant under a change of coordinates. So it's really important to remember that a vector and a vector's components are really not the same thing, and we should never confuse the two. So much like saying that a tensor is a multi-dimensional array of numbers, saying that a vector is just a list of numbers really misses the geometrical truth that lies behind the numbers in the list, right? Because vectors are geometrical objects that have geometrical meaning. So this definition isn't really very good. So let's try again, definition number 2. A vector is like an arrow, just like an arrow floating in space. So this is a more geometric answer. We can draw arrows and we don't really need to refer to a coordinate system in order to understand them. And just like before, we can add vectors together. To do this geometrically, we just place the tail of the second vector on the tip of the first vector like this. Some people call this tip-to-tail addition. And the resulting vector is just the vector that goes from the initial point on the first vector to the final point on the second vector. Another way of thinking about this is that we are creating a parallelogram using the vectors v and w, and the addition of v and w is just the vector that points to the opposite corner of the parallelogram. So that's vector addition under the arrow interpretation of vectors. And also, just like before, we can scale vectors. So if we take the vector w and scale it by 2, we would just get a new vector that points in the same direction but is twice as long. And again, we can do that with any other number like 5 or 3/4 or pi or whatever number we choose. Also, if we have some vector v and we scale it by -1, that means that we keep the vector length the same and just reverse the direction like this. So that's vector scaling under the arrow interpretation. So the arrow interpretation is pretty good. It makes it really easy to draw pictures and visualize vectors. You'll notice I've been using this interpretation all throughout the video series so far, and I plan on continuing to do that, but there is a problem here. And that problem is that not all vectors can be visualized as arrows. So unless you've studied a bunch of linear algebra, this might actually be a bit surprising to you, because a lot of teachers just teach vectors as if they are arrows floating in space like this. So these arrow type vectors are actually just a special kind of vector called a Euclidean vector. But there
Yeah,
are
of
other
course.
vector is a member of a vector space. The first thing is a set of vectors V, which are the vectors themselves. The second thing, S, is a set of scalars, so these are the things that we use to make vectors bigger and smaller. The third thing is some sort of addition rule that lets us combine two vectors together, so we could add, say, a vector V and a vector W and get some new vector V plus W, like this. And the fourth thing is some sort of scaling rule, which I'm denoting as dot, and that lets us use scalars on vectors to change their size. Usually instead of writing a dot, I just write the scalar right next to the vector, but you could put the dot there if you really wanted to. So really, what all this means is that vectors are things that we can add together using the plus addition rule, and that we can scale using the dot rule and a scalar. So this is a pretty abstract definition. There's no numbers that we can do number crunching with, and there's no pictures that we can draw. All we really have at the end of the day are a bunch of rules. So even though it's abstract, the reason this definition is so great is that there are a ton of things in math that can be added together and scaled. And even if we can't draw them as arrows, we can still apply vector rules to them. So if this definition seems a bit strange to you, I wouldn't worry about it much for now. I think it will make more sense in the future. For this video and many videos later on, we're just going to stick with Euclidean vectors since they're easy to draw pictures with and easy to visualize in our heads. So now that we have some idea of what a vector is, let's talk about how vectors behave under a change of coordinates. So you might remember from the previous video I had two coordinate systems, the old basis and the new basis, and we figured out the forward and backward transformations that let us move between them. So let's say we have a vector v sitting here in this space, and we want to figure out the vector's components. Well, since we have two different coordinate systems, we can measure v using two different bases. So let's start with the old basis e1, e2. How can we write v as a linear combination of e1 and e2? Well, it looks like we need one copy of E1 and 1.5 copies of E2. So I can write this out, V equals 1 E1 plus 1.5 E2. Now let's do the same thing in the new basis. So it looks like we use 1 E1 tilde and 2 E2 tildes. So V equals 1 E1 tilde plus 2 E2 tilde. And because I have the components now, I can write V as a column vector. So in the old basis, the components are 1, 1.5, and I've put a little EI down here to remind us that we're measuring in the old basis. And in the new basis, the components are 1, 2. And again, I've put a little EI tilde here to remind us that we're measuring in the new basis. Alright, so how are these two sets of components related to each other? Okay, let's think about that. Remember, with the old and new basis, the forward transformation f brings us from the old basis to the new basis, and the backward transformation b brings us from the new basis to the old basis. Now maybe that works with the components too, right? So let's try applying the forward matrix f to the old basis components and see what we get. Okay, so that's not right. So what happened here? Did we do the math wrong? Like, what's up? So this might sound crazy, but
So actually, the only thing that changes between the vectors is how much each component has on each line. So I think that the arguments would be not a matrix, not two matrix, but one giant vector with a bunch of vectors, and then multiplied by the matrix f would give the forward transformation. Yeah, but it's still two-dimensional because just separate each line. Yeah, because a vector of vectors is a two-dimensional matrix.
I'm going to suggest that we try using the backward transformation on the old coordinates instead. So let's give that a try. Okay,
But it's always the same vector, that's the thing. It's not a different one for each line. It's always the same vectors. So I think actually this is a little bit wrong. It would be more like aligned. More like a list of vectors. Kind of like that. These are vectors multiplied by f. So I think forward propagation would be. So I have the function that creates which is very simple, each vector. You just pass 2 arguments, then create torch.tensor with 2 arguments. Then I would have to make a list of this. And multiply by the f, which is the forward transformation. And the backwards transformation is just the transpose of f. Or f is the transpose of b. Or is it? It's kind of not. I'll have to go back and look, I think. Because he says it's the transpose, but here it doesn't look like it is.
So, by applying the backward transformation on the old components, we ended up with the new components. So for basis vectors, forward brings us from old to new and backward brings us from new to old. But with vector components, it's the opposite. Forward brings us from new to old and backward brings us from old to new. So what's up with that? Right? This might seem really weird at first, but it actually makes complete and total sense. And I would actually be a little bit worried if this wasn't true. So to understand why this happens, you'll have to check out the next video. So in the previous video, I left.
Yeah.
Hi everyone, so I'm gonna have to apologize for this, but I actually made a mistake in the previous video that I want to correct. So with the forward transform, everything I wrote on this slide is correct, except for the forward matrix, and the forward matrix should look like this. So notice how the coefficients from the first equation end up in the first column, and the coefficients from the second equation end up in the second column. In the previous video, I wrote it out like this, and that's actually F transpose, but the correct F matrix should look like this. And the same thing.
So the F matrix is, each column is in a E tilde, the E tilde vector. Which makes sense because the vectors would be a list multiplied by the matrix, which will make each column be one E tilde vector.
Thing goes for the backward transform. The first equation goes into the first column, and the second equation goes into
backwards one is the one that's kind of confusing to me. How I'm gonna do this in computation. It's the same thing, but
into the second column. In the previous video, I also accidentally wrote out B transpose instead. So looking at these equations for the forward transform, F12 tells us how much of E1 is in E2 tilde. And likewise, Fji tells us how much of Ej ends up in Ei tilde. In the previous video, I accidentally wrote this with F.
Fji tells how much Ej has in I tilde.
Ij instead, but that's wrong. So this should be Fji. And the same goes for the backward transform. Bji tells us how much of Ej tilde ends up in Ei. So these are the correct forward and backward transforms here. And I'd just like to clarify that the actual letters I use for the indexes don't really matter. What's important here is that the index that we do the summation over is the first letter of the forward or backward transform, and it corresponds to the index of the basis vector that we're transforming. The second index of the transform corresponds to the output basis vector. Again, I apologize for making a mistake like this right at the beginning of a video series, but hopefully you aren't too confused. For the rest of the video series, I'm going to be using these equations here.
Welcome back to the video series on tensors. In the last video, we covered forward and backward transformations, and in this video, we're going to talk about our first example of a tensor, which is the vector. So what is a vector exactly? Much like tensors, you might get different answers to that question. Kind of vector called a Euclidean together using the plus addition rule, the old basis and the new basis, and we figured out the forward and backward transformations that let us move between them. So let's say we have a vector v.
It's just confusing because I don't know the relationship between this backwards and forwards.
Sitting here in this space, and we want to figure out the vector's components. Well, since we have two different coordinate systems, we can measure v using two different bases. So let's start with the old basis e1, e2. How can we write v as a linear combination of e1 and e2? Well, it looks like we need one copy of e1 and 1.5 copies of e2. So I can write this out, v equals 1 e1 plus 1.5 e2. Now let's do the same thing in the new basis. So it looks like we use 1 e1 tilde and 2 e2 tildes. So v equals 1 e1 tilde plus 2 e2 tilde. And because I have the components now, I can write v as a column vector. So in the old basis, the components are 1, 1.5, and I've put a little ei down here to remind us that we're measuring in the old basis. And in the new basis, the components are 1, 2. And again, I've put a little ei tilde here to remind us that we're measuring in the new basis. All right, so how are these two sets of components related to each other? Okay, let's think about that. Remember, with the old and new basis, the forward transformation f brings us from the old basis to the new basis, and the backward transformation B brings us from the new basis to the old basis. Now maybe that works with the components too, right? So let's try applying the forward matrix F to the old basis components and see what we get. Okay, so that's not right. So what happened here? Did we do the math wrong? Like, what's up? So this might sound crazy, but I'm going to suggest that we try using the backward transformation on the old coordinates instead. So let's give that a try. Okay, so by applying the backward transformation on the old components, we ended up with the new components. So for basis vectors, forward brings us from old to new and backward brings us from new to old. But with vector components, it's the opposite. Forward brings us from new to old and backward brings us from old to new. So what's up with that? Right? This might seem really weird at first, but it actually makes complete and total sense. And I would actually be a little bit worried if this wasn't true. So to understand why this happens, you'll have to check out the next video. So in the previous video,
Hope he talks about the relationship thing forward and backwards again. So I think what I need to do is a function for a forward matrix and a function for backwards and the function for each vector. And then I can use those functions to build whatever transformations I want. So I think I'm gonna search for this stuff now.
Let us print x dot. Save again. Okay. Let us run and see it. So here we are saying,
And temporarily I'm gonna make the backwards function equal to the transpose of the forward one until I understand the relationship better. Also, gonna search for how to get the transpose.
just change row to columns and columns.
Tensor.transpose is right there. Tensor.transpose.
To row. Okay. So this will be 2 cross 4, whereas this will be 4 cross 2. Okay. So let us run and see it. See, it is 2 cross 4 and we got 4 cross 2. Now, if we have a tensor which is more than 2 dimensions, we cannot use a tensor.t method. Okay, and for that we need to use tensor.transpose. For example, here we have a tensor has a dimension of like 3 cross 2 cross 4, and if we want to transpose like a dimension first to third, we cannot do that with tensor.t. We need to use tensor.transpose. Okay, so let us try to do that here. So let us amend this out. So here we can simply say x is equal to x dot transpose. And one more thing is to remember, like tensor.t doesn't accept any argument, whereas in transpose we need to pass the argument like which particular axis we want to exchange with which particular axis. Okay, so here, for example, if you want to exchange this axis with say this axis, then we will say 0 versus 1. Okay, so we can simply say 0 1, and if you let us say print x dot shape, what the shape will be? It will be like 3 cross 2 cross 4. Okay, so 3 is like these subtensors. Okay, and then we have 2 rows in this particular each subtensor, and then we have 4 elements in each row. Okay, so that's why we get 3 cross 2 cross 4. Okay, so let us see what we get when we transpose 0 to 1. So what we have is 3 cross 2 cross 4. Now 3 is replaced with 2 and 2 is replaced with 3. Okay, so we will get a tensor of 2 cross 3 cross 4. Okay, so x dot save. So let's run and see it. So you see we had a tensor of 3 cross 2 cross 4, and then when we changed this and this, replaced 2 is went here and 3 went here. Okay, and also let us we can say like 0 replaced with 2. Now in this case, this will be replaced with this and this will go here. Okay, so let's run and see it. You see, this went here and this went here. I hope that is clear. Now let's look at how we can use view, tensor.view. Okay, so let's say we have a tensor x is equal to torch.tensor. And let us say we have 1, 2, 3, 4, 5, 6, and then we have another one. Let us say 7, 8, 9, 10, 11, 12. Okay. Now if we want to change the shape of this tensor x, we can use view as well as reshape. And the main difference between view and reshape is like they function the same way, but there is a underlying difference. So view tensor is simply like it uses the same data. So when we use view to change the shape, it doesn't create a copy. It simply look at the same data source that the base tensor has. Whereas reshape actually it doesn't guarantee that. Okay, it might.
Welcome back, aliens. My name is Abhinvati, and let's continue the series on Python. Till this point, we have talked about functions, right? And we know now how to create functions. Now, again, when you have a big project and if you want to break down your project into smaller tasks, each task can be represented with the help of function, and those things are reusable. That's why we define in that one particular block, right? When you want to use a concept of modularity, we use a concept again of functions, and then we get modules, and we'll talk about them later in detail. Important point here is we're talking about functions, of course, we call them, right? So again, in this example, we'll focus on two things. The first one is how to pass a parameter to a function, and what happens with the variable when you pass it to a function. Okay, if you modify the value, what will happen? Again, we'll see that, and then we'll also see different types of parameters we can pass, or you can say arguments we can pass, right? So let's get started. Now let me define a simple function here. I will say def, and you can go with any function name, doesn't matter. I will say update. Okay, you can say modify or any function name, doesn't matter, right? So we have an update function. Now this update function will take a value from a user, and let's say the value is in a variable called as x. I love this variable name x. So we have a function which is update, and we are passing a variable x. Inside this update, I will be saying x equal to 8. Now you tell me if I update the value and if I print it here, of course will it get updated whatever value you pass? Let's try. What I'm talking about is if I call this function update by passing a value 10. So initially the value of x is 10, but later we are saying, hey, I don't want to use the value 10. I want to change the value to 8 and then I want to print it. So we print 8 or we print 10. So think about it. Of course, why did we print 8? Because we are updating a value, right? So let's run this code, and here we go. We got the output as 8, so it works. That's great. So we are getting the update value. What will happen to the value? Example, if I create a variable here outside this, if I say there's a variable called as a, and the value for this a is 10, and I'm not passing 10, I'm passing a. So basically I'm passing the value of a. So we are passing 10, right? The value of a is going to x now. Let's run this code. This works. Now let me print the value of a. So what do you think? What will happen now? Of course, the value of x. So this print will print 8, of course. What about this print? Will this print 8 or 10? That's a question, right? Because here we are printing the value of x. Let me just specify that explicitly there. So here we are printing the value of x, and here we are printing the value of a. So this is what we're doing, right? So let's run this code again. So what do you think? We'll update the value for a as well. And if you run this code, you can see a is still 10. So even if you're updating the value for x, it is not affecting a. So we have a concept called as pass by reference and pass by value. So if you have learned other languages like C, C++, we have this concept there, right? Pass by value and pass by reference. So what happens in Python? Is it call by value or call by reference? Let me just give you a thing what is call by value is. Now when you say you are calling a function by passing a variable value, it will be passed as a value, not as a variable. Example here, when I say update a, I'm not passing a, I'm passing 10. That's important, right? I'm passing the value of 10. Okay, I'm not talking about Python here. Okay, I'm talking about the, so even if you update that 10, it will not affect 8. That's referring to the same ID. So the moment you change the value, it will give you a new ID. In Python, what, and we have 20. Change the index number 1, I want to make it 25, so it should be 10, 25, and 30, that's what I want. Now changing the list, right, will it change the ID? That's the question. Let's print the list here as well, and let's run this code, and you can see we got the updated value here, that's perfect, and it is also updating the original list, is it? Yeah, it's updating the original list as well, because the ID is same, right?
I think I need to watch more videos in order to understand what's gonna be, to get a sense of the bigger picture, because it doesn't make sense to create a function just to make a matrix. If PyTorch probably already has that function built in to the module, so, and if I don't know the values, if they're how it's gonna be correlated, then yeah, I can't see exactly if it's gonna be necessary to do this.
Video, I left off with this mystery of why vector components transform in the opposite way compared to our old and new bases. And I said that this makes a lot of sense. So let's talk about why that is. So here I have an old basis, E1, E2, and I have a vector v living in this space. And the components of v look like they're about 1, 1 in the old basis. Now what would happen if I increase the size of the basis vectors by a factor of 2? So I make them twice as big, right? So what if I said E1 tilde equals 2E1 and E2 tilde equals 2E2? Well, the new coordinate system would look like this, right? Where the basis vectors are twice as big. So what are the components of v in the new basis? Well, it looks like they're about 1/2, 1/2. So while the basis vectors grew by a factor of 2, the vector components shrunk by a factor of 2, right? They did the opposite thing. And this makes a lot of sense because even though v doesn't change, right? V is invariant. V looks smaller when we measure it using the new basis vectors because the basis vectors, the measuring sticks that we're using, got twice as big. All right, so here's another example. Again, we have the old basis E1 and E2 and the vector v, and just notice that v is made up of about equal parts E1 and E2. So the angle v makes with E1 is about the same as the angle that v makes with E2. And this means that the components in each direction are about the same. Now, what would happen if we rotated the basis clockwise? Okay, so the new basis would look something like this, right? Now, what about the components of V? Well, if you look at the angles, the angle V makes with E1 tilde is actually bigger than the angle V makes with E2 tilde. So again, V is invariant, it hasn't moved, but now it's leaning closer to E2 tilde compared to E1 tilde. And that makes it feel like it's rotating counterclockwise because the angle it makes with the second basis vector got smaller. Okay, so again, the components did the opposite thing. The basis rotated clockwise and the components rotated counterclockwise. So going back to this diagram, when vector components behave the opposite way that basis vectors do, that actually makes perfect sense. When the basis gets bigger, the components will shrink. When the basis rotates one way, the components will rotate the other way. Whatever the basis does, the components do the opposite. So now we have some intuition as to why this sort of opposite behavior happens in 2D. Let's see if we can prove it in any dimension. So let's just recall that we have two ways of writing V. We can write it as a linear combination of the old basis vectors with the coefficients being the old components, or we can write it as a linear combination of the new basis vectors with the coefficients being the new components. And we can also write these as summations just to save some space. Alright, so both of these summations are equal to V. Now let's bring out our forward and backward transformations here. So if we take the old basis and old components, what we can do is we can use the backward transformation to replace the old basis vectors with the new basis vectors. And so we get that, and rearranging the summations, we get this. So now we have V written as a summation of the new basis vectors. So what's this part in the middle? Well, if you look up here, when we write V as a summation of new basis vectors, the coefficients have to be the new components V tilde. So this here is equal to V tilde. So we've proven here that to move from the old components to the new components, we actually use the backward transformation, which is what we expected. And the same is true in the other direction. We can start with the new components and basis vectors, then replace the new basis vectors using the forward transformation, and that gives us a linear combination of old basis vectors. And again, this part in the middle has to be equal to the old coefficients. So we've shown here that when we go from the new components to the old components, we transform using the forward transformation. So these formulas here sum up everything we've learned so far. We know how the basis vectors transform, and we know how vector components transform, which is in the opposite way. Now, because vector components behave contrary to the basis vectors, we say that vector components are contravariant. And we'll see later that vectors are contravariant tensors. So I'll talk more about what that means later. One last thing I'm going to mention. So here you can see we've written the vector V as linear combinations of the old and new basis. But these vector components, since they are contravariant, we're going to make a small change in the way we write them. What we're going to do is, instead of writing these little I indices below the V, we're going to switch that up, and we're going to write the indices above the V instead. And this reminds us that the components are contravariant. Okay, since the basis indices are at the bottom and the vector component indices are on top, it's sort of a reminder that they behave in opposite ways. Now, you might be a bit worried that you'll confuse these upper indices with exponents, right? Because exponents sort of look the same. But exponents pop up so rarely when we're dealing with tensors that you can basically always assume that these are vector indices and never exponents. Alright, so that finishes up our discussion of vectors. In the next few videos, we're going to talk about covectors, which are another example of a tensor.
It's easy to understand, but it's really hard to think about how to do this with coding.
In the last couple of videos, we saw our first example of a tensor, which was the vector, and we saw that vector components transformed in the opposite way that basis vectors do. And because of that, we said that vectors were contravariant. In the next few videos, we're going to talk about our second example of a tensor, which is the covector. So the first thing we're going to do is we're going to answer the question, what is a covector? Well, as a starting point, we can think of covectors as basically like being row vectors. And you might think, well, row vectors aren't too hard. A row vector is just like a column vector that we take and flip on its side like this, right? Well, it's not quite that simple. You might not be aware of this, but column vectors and row vectors are fundamentally different types of objects. And the reason you might think that they're basically the same is that you've normally been dealing with them in an orthonormal basis, which is a basis where all the vectors are 1 unit long and they're all perpendicular to each other. So when we're dealing with an orthonormal...
I'm search how to make a matrix with PyTorch. Before I continue. It's probably just do a nested list, and that's a matrix, but I wonder if there's a function for that.
Hey guys, welcome back to the channel and this new tutorial on PyTorch. So in previous video, we learned about like how we can extend the NN module of PyTorch, and then how we can create a simple model using that. And then also we saw like how we can create a model using that, and then how we can pass the input to the model and how we can get the output. Okay. So in this video, we will continue and learn about another important module, which is a linear module, also known as a simple neural network. So in simple neural network, we have input, which is here input data x. It has 4 elements, and then we create a weight matrix, okay, which is also like a learnable parameter, we could say, known as transformation. So what we do is we simply...
Basic tensor operation is an essential part of PyTorch, and it's worth to spend some time to learn it, and it's probably the first thing you should do before you do anything related to deep learning. What is going on, guys? Hope you're doing awesome. And in this video, we're going to go through 4 parts. So we're going to start with how to initialize a tensor, and there are many ways of doing that. We're going to go through a lot of them, and then we're going to do some tensor math and comparison operations. We're going to go through tensor indexing, and lastly, we're going to go through tensor reshaping. And I just want to say that I really encourage you to watch this video to the end so you get a grasp on these tensor operations. Even if you don't memorize them after this video, and there's probably no way you can memorize all of them, you will at least know that they exist, and that will save you a lot of time in the future. So in this video, I will cover the basics, but I will also go a bit beyond that and show you a lot of useful tensor operations for different scenarios. So there's no way I'm able to cover all of the tensor operations. There are a bunch of more advanced ones that I don't even know about yet, but these are definitely enough to give you a solid foundation. So I guess we'll just get started, and the first thing I'm going to show you is how to create a tensor. So what we're going to do is we're going to do my tensor, and we're going to do torch.tensor, and we're going to do, the first thing we're going to do is a list, and we're going to do a list inside that list. We're going to do 1, 2, 3, and then let's do another list, and we're going to do 4, 5, 6. So what this means right here is that we're going to do 2 rows. So this is the first row, and then this is the second row. All right. So we're going to have 2 rows in this case, and we're going to have 3 columns. So what we could do then is we could do print my tensor, and we can run that, and we're going to just get in a nice format. So we're going to get 1, 4 for the first column, 2, 5, and 3, 6. Now what we can do as well is we can set the type of this tensor. So we can do dtype equals torch.float, and we can do, let's say, float 32. So then if we print it again, we're going to get that those are float values. Now another thing we can do is we can set the device that this tensor should be on, either CUDA or the CPU. Now if you have a CUDA enabled GPU, you should almost always have the tensor on CUDA. Otherwise you're going to have to use the CPU, but we can specify this using the device. So we can do device equals, and then we can set this to CUDA if you have that available. And then if we print my tensor again, we can see that the device says CUDA right here. If you do not have a CUDA enabled GPU, then you're going to have to write CPU right here. I think that CPU is also the default, so you don't have to write it, but it can help to just be specific. Now, if we run this, the device doesn't show, which means that it's on the CPU. You can also set other arguments like requires gradient, which is important for AutoGrad, which I'm not going to cover in this video, but essentially for computing the gradients, which are used when we do the backward propagation through the computational graph to update our parameters through gradient descent. But anyways, I'm not going to go in depth on that. One thing we can do as well is that you're going to see a lot when in my videos, and just if you read PyTorch code, is that people often write device equals CUDA if torch.CUDA is available, like that, else CPU. All right, and in this case, what happens is that if you have CUDA enabled, the device is going to be set to CUDA, and otherwise it's going to be set to the CPU. Kind of that priority that if you have enabled, then you should use it. Otherwise, you're going to be stuck with the CPU, but that's all you have. So what we can do instead of writing the string here is that we can just write device like this. And now the great thing about this is that two people can run it, and if one has CUDA, it's going to run on the GPU. If they don't have it, it's going to run on the CPU. But the code works no matter if you have it or not. Now let's look at some attributes of tensors. So what we can do is we can, as I said, print my tensor, and we just so we can do that again, and we just get some information about the tensor, like what device it's on and if it requires gradient. What we can also do is we can do my tensor, and we can do .dtype. So that will just in this case print torch.float32, and we can also do print my tensor.device. And what that's going to do is going to show us what device the tensor is on, so CUDA, and then you're going to get this right here, which essentially if you have multiple GPUs, it's going to say on which GPU it's on. In this case, I only have one GPU, so it's going to say 0, and 0 I think is the default one if you don't specify. And then what we can do as well, we can do print my tensor.shape. So yeah, this is pretty straightforward. It's just going to print the shape, which is 2 by 3. What we can do as well is we can do print my tensor.requires grad, which is going to tell us if that tensor requires gradient or not, which in this case we've set it to true. All right, so let's move on to some other common initialization methods. What we can do is if we don't have the exact values that we want to write, like in this case we had 1, 2, 3, and 4, 5, 6, we can do x equals torch.empty, and we can do size equals, let's say, 3 by 3. And what this is going to do is it's going to create a 3 by 3 tensor, and or matrix, I guess, and it's going to be empty in that it's going to be uninitialized data. But these data values that is going to be in this matrix are going to be just whatever is in the memory at that moment. So the values can really be random. So don't think that this should be zeros or anything like that. It's just going to be uninitialized data. Now, if you would want to have zeros, you could do torch.zeros, and you don't have to specify the size equals. Since it's the first argument, we can just write 3, 3 like that, and that's going to be. So what we can do actually, we can print. Let's see, we can print x right here, and we can see what values it gets. And in this case, it actually got zeros, but that's not what's going to happen in general. And yeah, if we print x after this, it's also going to be zeros. Now, what we can also do is we can do x equals torch.rand, and we can do 3, 3 again. And what this is going to do is it's going to initialize a 3 by 3 matrix with values from a uniform distribution in the interval 0 and 1. Another thing we could do is we could do x equals torch.ones, and we can again do, I don't know, 3 by 3. And this is just going to be a 3 by 3 matrix with all values of 1. Another thing we can do is torch.I, and we're going to send in 5 by 5 or something like that. And this is going to create an identity matrix. So we're going to have ones on the diagonal, and the rest will be zeros. So if you're curious why it's called I, is because I, like that, is the identity matrix, how you write it in mathematics. And if you say I, it kind of sounds like I. Yeah, that makes sense. So anyways, one more thing we can do is we can do something like torch.arrange, and we can do start, we can do end, and we can do step. So, basically the arrange function is exactly like the range function in Python. So this should be nothing weird. One thing I forgot to do is just print them so we can see what they look like. So if we print that one, as I said, we're going to have ones on the diagonal and the rest will be 0. If we print x after the arrange, it's going to start at 0. It's going to have a step of 1, and the end is non-inclusive, the fifth value, or 5. So we're going to have 0, 1, 2, 3, 4. So if we print x, we're going to see exactly that, 0 and then up to inclusive 4. Another thing we can do is we can do x equals torch.linspace, and we can specify where it should start. So we can do start equals 0.1, and we could do something like end equals 1, and we could also do step equals 10. So what this is going to do is this should be steps. So what this is going to do is it's going to start at 0.1, and then it's going to end at 1, and it's going to have 10 values in between those. So what's going to happen in this case is it's going to take the first value 0.1, then the next one is going to be 0.2, 0.3, 0.4, etc. up to 1. So just to make sure, we can print x, and we see that that's exactly what happens. And if we calculate the number of points, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So we're going to have equal to steps amount of points. So then we can do also x equals torch.empty, as we did for the first one, and we can set the size, and I don't know, 1 and 5 or something like that. And what we can do then is we can do dot normal, and we can do mean equals 0 and the standard deviation equals 1. And essentially, so what this is going to do is it's going to create the initialized data of size 1 by 5, and then it's just going to make those values normally distributed with a mean of 0 and standard deviation of 1. So we could also do this with something like, with the uniform distribution. So we can do dot uniform, and then we can do 0 and 1, which would also be similar to what we did up here for the torch.rand. But of course, here you can specify exactly what you want for the lower and the upper of the uniform distribution. Another thing we can do is torch.diag, and then we can do torch.ones of some size, let's say 3. It's going to create a diagonal matrix of ones on the diagonal. It's going to be shape 3. So essentially, this is going to create a 3 by 3 diagonal matrix. Essentially, this is going to create an identity matrix, which is 3 by 3. So we could have just as well used I, but this diagonal function can be used on any matrix so that we preserve those values across the diagonal. And in this case, it's just simple to use torch.ones. Now, one
normal basis, the idea of flipping column vectors onto the side to get row vectors is actually true, but it's not true in any other coordinate system. And to realize why, we're going to have to think about row vectors as functions. So we can think of a row vector as a function on a column vector. So in this example, this row vector 2, 1 would be the function, and this column vector 3, -4 would be the function's input. To find the output value of the function, we just do the standard matrix multiplication or dot product of this row and column vector. So carrying that out, we get 2 times 3 plus 1 times -4, and that's just 6 minus 4, and then we get the output 2. Now, if we have any general covector alpha acting on any general vector v, then we get the output value by taking the dot product of the two vectors like this, and we can write that more compactly using this summation. So ultimately, we should think of row vectors as functions that take an input from some vector space v and return a real number or a scalar. Okay, so let's examine how these row vector functions work a little bit more. Let's say that we have a row vector which is acting on two vector inputs that are added together. So there are two ways that we could go about calculating the output. One way is to distribute the row vector to each of the inputs and then add the results, and that gives us this output here. And the other way is to add the inputs together and then get the row vector to operate on the column vector input. And you can see that this gives us the same output 5 as we had in the previous example. So row vectors as functions have this property here where we can add the inputs before or add the outputs after, and we'll get the same result. Another idea we can consider is what if the vector input is scaled by some number like this. And again, there are two ways that we can compute the output. We can scale the input vector and then have the row vector act on the result to get this. Or we can put the scaling number out in front and then scale the results of the row vector acting on the column vector. And again, we get the same result. So row vectors as functions have this property that we can scale the input or scale the output, and we get the same result. So to sum up, a covector is a function that takes a vector and produces a scalar or a number, and it has the property that we can add the inputs or add the outputs to get the same answer, and it has the property that we can scale the inputs or scale the outputs by the same amount and get the same answer. More generally, these two properties, when they work together, look like this. And this behavior of being able to add or scale either the inputs or the outputs and getting the same answer is called linearity. So covectors are linear functions. So now, how do we visualize these covectors? We know that we can visualize ordinary vectors as arrows like this. And we sort of could do the same thing with covectors, but that's sort of an awkward thing to do for visualizing a function. And it turns out there's a much better way to do it. So let's start by thinking of this 2D row vector as being a function on two variables, x and y. So the row vector 2, 1 can really be thought of as a function 2x plus 1y. So how can we visualize a function of two variables that produces one output? Well, this is very similar to a problem that map makers have to deal with when they want to convey elevation on a two-dimensional sheet of paper, right? When you have a topographic map, you basically need to show off the slopes of mountains and valleys, but only using a 2D page. So what topographers do is they take a map and they draw curves of constant elevation, like this. So this curve here that's labeled 3,000, everywhere on this curve is exactly 3,000 feet high. And this curve over here labeled 2,000, everywhere on this curve is 2,000 feet in elevation. So just looking at this map here, we know that when the lines are stacked together really densely, like over here, this is a place where the elevation changes really steeply, right? Whereas over here, where the lines are less dense, this is a comparatively shallow slope because the elevation changes less quickly. Another way of thinking about this is that if we have this red mountain here, if we take a horizontal slice at some height, we'll end up with contours that look different, right? So if we slice at this elevation, we'll get this contour. If we slice at this elevation, we get this contour. And this elevation is this contour. And these would be like the curves of constant height on a topographic map. So let's take this idea and apply it to the row vector 2, 1, which again, when taken as a function of inputs x and y, gives us the value 2x plus 1y. So to start, let's ask, where does this function equal 0? Well, if we change this around a little bit, we get the line y equals minus 2x. And that would be a line like this. And next we'll do where the function equals 1, so we get y equals negative 2x plus 1. And that would be a line with the same slope, but just shifted up a little bit. And when the function equals 2, we'll get another line just shifted up by 2 units instead. And so when this function equals negative 1, we'll get the same line just shifted down. And when the function equals negative 2, same thing, just shifted down even lower. Okay, so let's clean this up. So this is our covector 2, 1, visualized as stacks of lines. And note that since the stack is increasing toward the upper right, we can add these little arrows here to remind us of the direction of increase, right? This stack has a direction. It's increasing this way and decreasing the other way. And you'll notice that if I were to draw the vector 2, 1 as an arrow here, the arrow would be perpendicular to all the lines in the stack. Alright, so we can visualize covectors as stacks of lines, and this ends up being really useful, and I'll show you why on the next slide. Okay, so here I have the same covector alpha over and over again, visualized as a bunch of directed stacks, and over this covector I have the vector v in yellow pointing.
I have to think about... I think I'll have to watch the playlist probably multiple times. I have to think about what are the fundamental blocks that I'm trying to abstract into functions, because the main goal is going to be to code the special general relativity equation, and I can't remember really well. I know that the transformations are important, Lorentz transformations, but I just don't, from the way that he explains, it's really hard to think about the way to generalize things because he's using specific numbers to define things. And I'm trying to think about ways to put functions that don't depend on specific cases, but are kind of like general blocks that I can build upon to build the last equation later on.
In different directions. And what I'd like to do is I'd like to figure out the numerical value of the covector alpha acting on the vector v. So let's take a look at this first one here. So remember, each line in the stack is a line of constant value. So to get the value of alpha acting on v, all I need to do is count the number of lines that v pierces. So here v pierces 1, 2 lines. So the value of alpha of v would be 2. Okay, in this one it doesn't pierce any lines, but it gets halfway to the first one, so we would say 0.5 or 1/2. Here it pierces 1, 2, 3 lines, but it's going against the orientation of alpha, so that means that alpha of v is -3. And in this last example here, the vector is parallel to the stack, so we get a value of 0 since the vector doesn't pierce any lines at all. So this visualization is really nice, right? We don't need to know anything about coordinate systems or components in order to understand how a covector acts on a vector. We just look at the picture and count the number of lines the arrow pierces, and then that's the answer. Okay, so hopefully this is simple enough. Let's start thinking about ways we can modify covectors to get new covectors. So we have this covector alpha here again, and it acts on vector v to give a value of 2. Now if I asked you to make this covector twice as big, what would you do? Right? Maybe you should pause the video for 10 seconds and think about it.
Pythagoras.
Okay, so if we're looking for a covector that's twice as big, what you might be thinking is, well, if I want the covector to be bigger, then I just spread out the lines and make the space between them nice and big, right? But actually no, what we want to do is make the stack denser, because when we make the stack denser, it increases the value of alpha of v, right? So when we pierce alpha with v, we get 2. But when we pierce 2 alpha with
So that's the problem. How do I abstract this notion of covariant and variant vectors
v, we get 4, because there are 4.
with the plane? Because I need to put this into coding, into a function. Maybe it's as simple as making the scalar as an argument and then doing the inverse as a multiplication, but
4 lines that are pierced. So applying 2 alpha to v is the same thing as applying alpha to v and then scaling the result by 2. Now what if we wanted to shrink alpha to half its size? Well, you probably already know the answer. In this case, we spread the lines out so that they are half as dense. And now when we apply 1/2 alpha to v, we get a value of 1 because it only pierces 1 line. And again, that's the same thing as applying alpha to v and then scaling the result by 1/2. Okay, so that's scaling covectors. Now what about adding them together? So here I have 2 covectors, beta and gamma. Beta of v is 3 and gamma of v is 2. Now let's say I want to add beta and gamma together, so what would I do? Well, what we do is we create a new stack that has the same density as beta in the beta direction and the same density as gamma in the gamma direction. Okay, so I'll show you what I mean by that. Here's the new covector beta plus gamma, and you'll notice in the beta direction v pierces 3 lines, 1, 2, 3, and in the gamma direction v pierces 2 lines, 1, 2, which is just what we had before. So in a sense, beta has a horizontal density of 3 and a vertical density of 0, whereas gamma has a horizontal density of 0 and a vertical density of 2. And beta plus gamma, which is both of those combined together, it has a horizontal density of 3 and a vertical density of 2. And you'll notice that the vector v actually pierces 5 lines, which is 3 plus 2. So when we add covectors like this, applying the added covector to v gives us the same result as when we apply the individual covectors and then add the results. So that's adding covectors. Okay, so what we've done here is that we've shown that covectors have sensible scaling and adding rules. And what did I say before about things that we can add and scale? What does that mean? It means that we have a vector space, right? So if we have some ordinary vector space v with the scalars and the adding rules and the scaling rules, the set of all covectors which act on the vectors of v form a new vector space called the dual space, which we denote by v star. And this has a different set of adding rules, which I'm calling red plus, and a different set of scaling rules, which I'm calling red dot. And the reason I'm writing these rules in different colors is because they're actually different rules, right? The black rules are for adding and scaling vectors, like we did with arrows, and the red rules are for adding and scaling covectors, like we did with the stacks of lines. Okay, so the elements of v star are covectors, which are functions that go from v to the real numbers. The new scaling rule, which is the red dot, says that we can scale a covector by some number n just by applying the covector and then scaling the result by that number n. And the addition rule red plus says that we can add covectors by applying each one to the vector and then adding the results. So I'm not going to keep writing these in red. I just wanted to be very clear that the adding and scaling rules for these two vector spaces are different. Okay, so to sum up, covectors are functions from vectors to the real numbers. These functions have the properties that we can add and scale the inputs or add and scale the outputs to get the same answer, and that's called linearity. So these are linear functions. The set of all covectors that act on a vector space V together form the vector space V star, and these covectors have their own adding and scaling rules. And finally, we can visualize covectors as oriented stacks of lines. So when a covector alpha acts on a vector V, we just count how many lines the arrow pierces to get the answer. That more or less sums up what a covector is. So
I think I'm gonna take a break and come back later. I'm very tired. I'll come back, I'm probably gonna watch this video. Yeah, I'm gonna take a break, then I'm gonna come back later probably. If I don't come back today, I'm gonna come back 2 days from now, I think. I won't be streaming tomorrow. So see you.